So for both BeH2 and H2O, right, BeH2 and H2O, we have this happening in terms of the molecular orbitals. And you can ignore these labels on the left-hand side, these letters here. These come from group theory. We skipped that chapter, or we're going to skip that chapter. But this has to do with the symmetries of the orbitals, relative to different symmetry operations. Anyway, if we're looking at BeH2 and H2O, what the difference here is the number of electrons that's in each molecule. Right, so in BeH2, the number of valence electrons we have is 4. So if we think about putting those 4 valence electrons into orbitals, they'll go in the 2 lowest energy orbitals. So we can compare the linear case with the bent case. In the linear case, the electrons would go here, and in the bent case, they'd go here, and actually in this py orbital decreases enough at 90 degrees that it becomes the lowest energy orbital. And so the molecule will go towards whatever's lowest energy. I mean, that's just a general principle of nature. And so for BeH2 with only 4 electrons, it favors this linear geometry because it leads to lower energy. Water, on the other hand, H2O, here we have 8 valence electrons. And we have to fit all 8 of these into our system. Okay, so we'll do this in green for water. Let me erase some of this stuff from the BeH2, just to make this a little bit easier to follow. All right. So if we look at the linear case, they go 1, 2, 3, 4, 5. Oh. My hand moves stuff around there. 5, 6, 7, 8, because this is a set of degenerate orbitals. Whereas for the bent case, they go 1, 2, 3, 4, 5, 6, 7, 8. Now, because this px or py, I mean, whichever orbital it was, this decreasing in energy, because it has this net decrease in energy, because this is an occupied orbital in water, the fact that this decreases in energy means we favor the left-hand side. We favor the bent. Now, it doesn't go all the way to 100, it doesn't go all the way to 90 degrees. We know that the actual bond angle is 109.5 degrees. And you can't predict the exact bond angle from this, sorry, not 105, 109.5, 104.5. It's a little bit less than tetrahedral geometry. And we can't, from this treatment doesn't necessarily allow us to predict that exact angle. But it does give us a sense of what's going on with the orbitals and how the overlap between these orbitals depends on the geometry of the molecule. And so that's a general principle that applies here, that geometry matters. Geometry, and I'll say symmetry, matters for orbital energies. So you'll have a chance in your homework to look at some additional examples of Walsh diagrams of slightly different systems, and use these concepts and apply them to a different sort of system.